Okay, so this is from yesterday or from the warm up, and we already did that earlier. So now you should have tried the homework assignment that started down here. The answers were online. I can show them to you real quick. This is the answers to 1 and 2. You can pause it so you can check it. These are answers in the back. Now this is minimum what you should have. Okay. You might have a little more work and stuff showing. Yeah, I don't know. Graphing calculator problems is not usually a lot of work to show, but I do want sketches of these graphs and important things labeled on them, and then your final answers. Okay. So I don't know how you're pulling number 10 off without a sketch. I think that's probably impossible. So I'm going to go over these problems real quick. First problem. Now, if you see trig and there's no reference to degrees, then you should be in radian mode. And so in general, we will be in radian mode. So it's kind of good default to go to. On the AP test, it's going to be all radians. We'll do some degree stuff these first few chapters, but then after that, we'll probably never do any more degrees in this class. Okay. So 5/7, parentheses, e to the third plus sine of 1.5, close the parentheses on the sign, and then close parentheses on the whole top. So you got to remember, now if you don't close all your parentheses, it's going to give an error anyway, so it's going to be hard to get away with accidentally. Now the cube root, it's the same thing as to the 1/3 power. Now if you do this, you're going to get it wrong, because it's going to raise it to the first power, give you 10 divided by 3, it's going to give you 3 and 1/3. So if your exponents are ever more than just a single number, you need to put parentheses around them. Otherwise, it won't happen correctly. So that should be the right answer. 2.843 or 2.844 rounded truncated. 3 decimal place accuracy. Okay, next one, we're going to put this equation into our... Now we got to put parentheses around the top, and then divided by square root of x squared plus 1, close parentheses on that. We're not going to graph it, okay? Let's go to the table, second table, and you could type these numbers in. Okay, now it's only showing, like I said, 5 digits, so you got to be careful because it is round the last digit it shows. But I think this is good enough for us, 0.635 or 0.636 if you round, 0.975 truncated or 976 rounded, 631 truncated or 632 rounded. So there you go. It's just helpful for doing lots of calculations for the same equation. Let's use table. Okay, so next one, we're going to sketch it. So that's actually something I'm asking you to do, and then you're probably going to do some work with it. So we get rid of that, and this is inverse tangent. Now make sure this is not an exponent, it's inverse tangent. It's a common notation for inverse functions. Little potentially confusing sometimes, looks like an exponent. X, close that, divided by square root of x squared plus x plus 1. Okay, we're going to go to window negative 10 to 10 for sure. I don't know what the y value should be. I mean, we'd start with negative 10 to 10 just to see what it looks like, and we might change it to make it look better, bigger, smaller. So there it is. Okay, I mean the height's way too big. You can barely see it. Okay, so this is a lesson to be learned that you need to be able to see what's going on. So I think maybe even -1 to 1 or something might be enough. Window. Now, by the way, let me show you something else. There's this other way of zooming in, and this seems like a good one to try it on. If you go zoom, at the bottom of the list is zoom fit, zoom 0. Quickest way to get to the bottom of the list, and your calculators go up from the top. Zoom fit, what it does is it takes your X values that you've put in the window, so it depends partly on what you put in, and then it pre-calculates all the values for those X values, finds all the Y values, and then refits the graph window to fit it perfectly. And it takes a little longer, but it gives you a nice view of the graph. Sometimes it backfires. If you have a graph that gets really big, like one end goes to infinity or something, and then your graph will be really big and hard to use. So it's not like a surefire thing. So if I do that, zoom fit, watch, it takes a while because it's pre-calculating all the values. Essentially, it's doing all the work twice. Then it resizes the y-axis. The x-axis is up to you and gives you this nice picture of it. So that's another option that I use sometimes if I don't really know what the y value should be. But sometimes I'm scared about it give me a really zoomed out graph just because the values get really high on one section. So we're going to sketch this, and it kind of looks like this. And it's like that. So label your axis, little arrow, so we know they're not like vertical lines or horizontal lines, which we have on some of these problems. So that's pretty good. Now, let's jump down to number 5 right now while we're at it. Find the maximum and minimum values of f of x in problem number 3 from -10 to 10. So, I mean, we can see it right here. This is your max value, absolute max. This is your min value, absolute min. And your calculator is really good at finding these for you. So we do second calculate min. Now you got to tell it where to look for it. And kind of the more narrow of an area you give it, the quicker it can find it. So, I mean, this one looks like it's around like -1 or -2. So I might say, oh, let's look from -4 to 0 and guess -2. It doesn't have to be like perfect or anything, but that's pretty good. Let's write that down. -1.102329, comma, -0.79063333. And I'm just writing these extra decimals down because what if I need these for a future calculation and I don't want to go back and redo this. Second calculate number 4, maximum. Looks like it's around 2. So maybe 0 to 4, guess at 2. So I just left bound, right bound. Something definitely to the left and right of it, but close. 1.2015192, comma 0.4591796. So I want you guys to sketch these pictures, label stuff, write max, write min. That's the only work you can show me. I don't need to see the buttons you pushed. But this tells me at least you kind of understand the basic idea. So we can say the maximum. Now, this is the way I want you to write these answers. The maximum is 0.459 at x equals 1.201 or 1.202 if you want to round. The minimum, I'm telling you, this is the way I want you to write it. This is going to pay off this year. The minimum is -0.790 or -0.791 if you round at x equals -1.102. So that's the way I want you to write these maximum and minimum answers. I'm telling you, people lose points on the AP test because they don't write them like this. And it's silly. It's an easy thing to. That's a very safe way because that answers the max and min. If you write them as ordered pairs, you don't get credit. Sorry, it's not. The x value is not the max or min, so putting the x value as your max or min is not the answer. But you could say, hey, this is where this is the max, and this is where it happens, which is important often and sometimes asked for. Okay, this is called piecewise graph. That means part of the graph is defined by this curve, and parts defined by this curve. Now, You can't really graph piecewise graphs perfectly, but we could graph them on here in a way that, could help us sketch the graph. So we'll put natural log of x in, and we'll put negative x plus 1. And the window, I don't know, we could go negative 10 to 10, negative 10 to 10, which is standard window, by the way. You could do zoom 6. And let's graph it. Now, that's a natural log graph, which I don't know. You guys should know natural log graphs look like this. We'll study them again just to make sure you're really good at natural log graphs in a future chapter. And then that's a line that goes through y-intercept of 1, has a slope of negative 1. Now, I feel like this graph isn't great. Like, I feel like we could probably cut off some of the information over here. This is where all the interesting stuff's happening. So I'm going to go to window and change my x min to negative 1 and my y max to like 4. It's just helpful to have a little more close-up view of the interesting stuff. Okay, so we're going to sketch this graph. Now, when I sketch piecewise graphs by hand without calculators, which we will be doing more of later on, I like to just sketch each graph, on its own lightly. Okay, so this is a natural log graph, roughly. Now, this is 1, by the way. So all natural log graphs go through 1, unless there's some shift or something. And then this other one's a line, which is going through 1, and it has a slope of negative 1, so it goes like that. So I'm just drawing this lightly. Now, it says that we got to break it up at E. Now, E is about 2.71, and your calculator has E on it, so you could always go over here and say, what's E? 2.718, okay? So that would be around right here, okay? E is a natural number. So that means at this point, this is where we switch from one curve to the other. To the left of it, or equal to it, solid dot, to the left of it is this line. So I'm going to darken in the portion of the graph. And then the other one, the line picks up here and it's an open dot. And usually you don't want to have two different definitions at the same point because then it's not a function. So one's going to be solid, one's going to be open usually. And darken that in. So this is my piecewise graph, the darkened portion. And we could leave the light one. So if you just make it really obvious to me. So this is a nice sketch of the piecewise graph. And I use my calculator to help me just to verify the shapes and stuff. Okay, so let's find the maximum value of this graph. Now this is where we have to intervene and be a little smarter than our calculator, because our calculator, we can't graph it like this, right? We know right here, this is the maximum value. That's the highest value on this graph, right? Of the resulting piecewise graph. And I mean, for sure, right? That's it. And so we don't need the calculator to tell us that that's where it is. That is exactly where it is. It's when x equals e, and you plug it into this function. So what we're going to do is we're just going to either use the table or go to the original screen, and we could delete previous values. And we're going to put e in here. And y1 is the natural log graph. And so the coordinates at this point are e comma 1, right? And that's your, so the maximum is 1.000 at x equals e, or 2.718. So that's how I'd write that answer. So, we didn't do the traditional max thing because our calculator wouldn't have found that for us, but we still use our calculator to help us. Okay, so here's some rational inequalities, which we're going to have some of those to do by hand on your next test, but maybe you'll have an opportunity to use your calculator to do one. And it's definitely worth it because that's a mess, and you're not going to pull that one off by hand because there's like trig mixed into it. So the best way to do this, I think, is to move this all to one side. This is what we do when we do it by hand, first step. So we're doing the same thing. But then I'd stop. I wouldn't try and give least common denominators and all that stuff. You could do that, but it's not going to help make anything easier. So So I'm going to enter this in. And let's see, they do give us a portion of the graph we need to focus on -10 to 10. And then I don't really know how big this graph is going to be, but I'm telling you, this graph is going to have some vertical asymptotes. So the graph's going to get really big. And so doing the zoom fit thing probably backfire. Let's just try it. Zoom 0. It's probably going to be a really tall graph, which is not going to be helpful for us. It's not terrible, but it doesn't need to be that tall. So, I mean, window, if you go to window, you'll see what it decided to make it. I mean, I think if we did -10 to 10, that might be good enough. Let's just try that real quick. Now, you should know that this has some vertical asymptotes and stuff, and you should, rational functions. So if we were to draw a sketch of this, you have the y-axis, right? You have the x-axis. And we're going to 10 and -10. Now we know it has a vertical asymptote at x equals 2, right? We usually draw vertical asymptotes with light dashed lines. Now my calculator actually draws them in, right? Okay, so, and then you're going to have one here when x equals sine x, which that's a little harder to figure out in your head, but it looks like it's 0 because sine is 0, 0, and 0. So I think it is actually going to be 0. That's going to be that other vertical asymptote, which is what it looks like this graph has. So these are things that you should look at this and be like, oh, that makes sense. Now, when you plug it, then over here, and then as you go to x gets really big, these denominators get really big and the whole thing goes to 0. Or if they get really negative, go to negative infinity, they get really big in the negative direction. And so it makes sense that there is a horizontal asymptote, y equals 0. But this is usually what rational functions do. They kind of go towards the vertical asymptote, blow up, positive or negative. Over here, it's kind of doing something funky like that. And then sometimes in between they go like this, but they usually change sign. So this one kind of goes like this. So it's getting closer and closer to. So anyways, now we want to know, where is this below the x-axis? Well, right here it looks like is the only chunk right there, right? And in fact, I don't even need to use my calculator to calculate these values because those are vertical asymptotes, which I know are 0 and 2. And that's your answer. And it's not going to have brackets because it doesn't actually equal 0 at the edges, okay? Because it never has a value at 0 and 2. Don't give me answers where the function doesn't exist. So this is what I would expect for that. Next one, like I said, I would move everything to one side. Compared to 0. Enter that as an equation. Math num absolute value, x squared plus x minus 2, close the absolute values, minus sine x. Make sure you're in radian mode. Okay. And then go to window, -10 to 10. I don't know how tall this is going to be. We could try the zoom fit thing, or we could just try -10 to 10 and then adjust from there. So there it is. Now, absolute value functions usually have some sharp corners, so no surprise here. So I think that looks good enough. So we're going to sketch it. I need these sketches to give you credit. Homework, test. Okay. And the graph looks kind of like this. I don't know. I should draw it a little better. I'm just trying to make sure I get the x-intercepts are what matters, right? And so we're saying, well, where is this below the x-axis? Open dots. This is the chunk of the graph right there. So we do need to use our calculator to find those x-intercepts. Second, calculate 0. and tells you where to look for it. So you know what? It might be good to zoom in here, but I don't know. Is that 0? That looks like it's 1. So maybe between 0 and 1, guess 0.5. Now it's going to show a flashing dot, so we'll know if we found it. I think we found it. 0.75181301, comma 0. Okay, and then the other one, so I can calculate 0. Looks like it's between 1 and 2. So 1 to 2, guess 1.5. And it is 1.2920373, comma 0. Now, it probably would be better that after you graph this, then you zoom in right there. You could do zoom box and create a box around those. And then you could see more clearly that, yes, it does cross. Yes, it does cross. And then, because sometimes they might cross more than times than you can even tell. So you might be good to zoom. But the answer is 0.751, comma 1.292, parentheses, because it wasn't or equals to. Now, if you rounded, the first one would be that. The second one would still be the same. So there you go. All right. Let's see. Region R is bounded. That means it's enclosed by all these different functions. So we're going to go here, enter these functions. Natural log of x, 5 minus x, and 0.25. Now, I don't really know what the window should be. We could start with zoom 6, negative 10 to 10, negative 10 to 10. Now, there's the natural log function. There's the line, and there's another horizontal line. So it's good to be like, oh, this graph looks like this, right? This is a graph that crosses at 5 and has a -1 slope, and then this one's just a flat line, right? And so you can see them all, and then you can say, oh, you know what? This is really the important area right here. So I'm going to change my window from, say, -1 to 5, and then maybe -5 to 6. -1 to 5, and -5 to 7. So you need to be good at just like readjusting. And I might even change this again. That seems pretty good. But this horizontal line, it looks like it's right on the x-axis, but it's just above it, just a tiny bit. Now, when I draw my picture, I might go ahead and exaggerate. I'm going to draw, I don't know, I guess we could draw the picture here. I'm going to exaggerate some of these things. Just, your picture doesn't need to be like perfect or anything. It needs to be relatively correct. But I'm going to say, okay, well, this is y equals 0.25. Okay. Which, by the way, I put this one in y1, y2, y3. Might be good to put a little note to yourself so you remember, because there's multiple curves here. And you have the natural log function. It goes like this. Okay. And so I'm going to label all these. And then we have the other function that crosses at some 5. And then it crosses. I'm just trying to make it look kind of right. Y equals 5 minus x. Right. So I drew that picture. I kind of exaggerate a little bit so I can see what's going on down here. Now, we're trying to find the equation of the tangent line to the natural log graph at x equals 3. Okay, so there's several ways to do that, to find the equation of the tangent line. Now, the equation of the tangent line, one way, the easiest way, I'm going to show you several ways because we've been doing all of these. You could go to the draw menu, second program draw, and go down to tangent. It's kind of a cool trick. I would definitely use it. And then you tell it where you want it at x equals 3. Ooh, shoot. Now, make sure you selected the right function. Now, I got lucky because my natural log function was the first one, and by default, it just goes to the first one. Otherwise, you got to toggle between them by going up and down. So there it is. And it's, I don't know, it's somewhere like around here or something. And so, anyway, so you could do, I don't know if you guys are writing little notes to yourself still. Second program, draw, menu. number 5, tangent, and then x equals 3 enter. So I mean, this is all the steps I took. And so the equation is y equals 0.333x plus 0.098 if you want to give 3 decimal accuracy, or 0.333x plus 0.099. One of those. That's a quick, easy way. The other way is to find the slope, which we've done. So this is the first time I think I asked for the equation of the tangent line, not just the slope. So we could say, well, let's find the derivative, dy dx, and make sure you're on the right function. So if you go up or down, it changes which function you're trying to find the derivative of, okay? And you wanted x equals 3, so that'll give you the slope. So you could do that. You could say, okay, well, dy dx equals 0.333333335. And then to write the equation of any line, you need the slope and a point. Going back to algebra 1, how do you write the equation of a line? You need slope and a point. We have the slope. The point would be second calculate value, or go to the table and type 3 in, and then it'll tell you what the XY pair is right there. So that's the point, you know. So 3, 0.1986123. And then the way that we're going to write equations of lines all the time is point slope form. So we could do y minus 1.098 equals the slope 0.333 times x minus, right? So the point slope form, y minus y1 equals m times x minus x1. We're going to use that all the time. And this would be actually an okay equation answer. You don't have to do it in slope-intercept form. Now, you could change this slope-intercept form if you needed to for some other reason, which sometimes there's good reasons to. But if that's the answer, then that's... So, I mean, either one of these, this should give you the same thing. Now, the fact that I rounded truncated 3 decimals in the middle of my work, and then if I go to change the slope-intercept form, it might actually be different. Okay, now number 10 says find the area of region R, which is the region bounded by all these. So that's this region here. It's 3 different curves. So one of the things we need to do, I think, is figure out where this region starts and ends. So we got to find those intersections. I also think we need to find the intersection here, because you're gonna have to get a little creative geometrically. Okay. Remember that integrating, which is what we're going to use, finds the area under a curve. So we're going to find the area under this curve, and then the area under that curve, and then subtract this area from both of those to get what's left inside. Okay, so that's my strategy. So I'm going to do, my strategy is I'm going to do this area plus this area minus that rectangle on the bottom to get the leftover area. So that's my game plan right there, which I don't think is a bad idea to write. But we definitely need all these intersection points. So let's go and find them all and write them on our curve, write them on our picture. So second calculate number 5, intersect. Now you got to figure out which curves you're doing. If I do the natural log curve, and then I do the line like that, hit enter, and I guess I was close enough that I just used a cursor. That's that top one. It's just going to show blinking dot where it's at. So this is 3.6934414, comma 1.30655586. Okay, then we're going to do it again. Second calculate number 5, intersect. Now the first curve I could do natural log, but then I don't want to do this line again. So I go up or down to select the other line, and that's going to give me the one I think over here, right? No, it's going to give me this one. So even if I start way over here, it'll eventually find it. It'll just take longer. So the closer we get, now I'm just using cursor because I don't remember what these x values are, just to get close to it. So that one is 1.284024, comma 0.25 Write this all down in your picture so you don't have to redo it later. So you can calculate number 5. Now I don't want the natural log curve. I want the two lines. This line and that line. And then their intersection is way over here. Again, I usually don't do this because it takes forever. And it is 4.75 comma 0.25. All right. So that's some good information. Now, I need the setups for integrals to get full credit. This is also true on the AP test. So I'm trying to train you now. Setups are the calculus notation. We're going to let our calculators do all the calculus for us. So if we integrate from 1.2840254, you want more than 3 decimals in your work, to 3.6934414. In this graph, that's going to be the natural log graph. So I'm going to put that in there. So that gives me that first chunk plus. Now this one starts at 3.6934414 and goes to 4.75. It's the x values we care about. And that's the line 5 minus x, which you need to put in parentheses because it has multiple terms, and you got to put the dx's on these. Minus you could do this whole big rectangle at once, or you could do it in 2 separate chunks. It's up to you. I mean, it's quicker once. 1.2840254 all the way to 4.75 of 0.25 dx. This is the setup, and this should give us the answer that we're looking for. Now, there are some things that you could do to kind of shortcut this. You could be like, hey, this is just a rectangle. Instead of doing this, the height is 0.25, right? I'm just do base times height. The base is the distance between 4.75 and 1.2840254 times the height is 0.25. So you could do that. I mean, that's essentially what your calculator is going to do. This, in fact, right here is a triangle or a trapezoid. So you could do trapezoid on it. I don't really know if it's going to save that much time. Your calculator can do these things very nicely. It's still pretty messy. So it's up to you. Now, I personally wouldn't do these on the graph screen because it's going to take a lot of time to do each separate section, write them down, go to the home screen. So I usually like to do everything on the home screen, especially with multiple curves. So I'm going to do math 8. Nope. Math 9. So you're going to start to remember these. You could do, they're near the bottom list. So you could go there and select them, or you could just hit the number. Now the first one, this is vars y-vars function y1. That's one thing you could do, or you could retype it. Natural log it's not that bad. Comma x, comma 1.2840254, comma 3.6934414. Okay, that's the first one. And we can do these all at once. Plus math 9, vars y-vars function y2. Double check up there. Yeah, that's what we put in y2. Okay, comma x, comma 3.6934414, comma 4.75, and then we do the last one minus math 9 vars y-vars function y3, comma x, comma 1.2840254, comma 4.75. So there's a lot typing, but this will give us the answer all at once. 2.051. Round truncated comes out the same. Otherwise, you could do each of these areas individually. And I think if you did, you get like 2.0952755. You don't want to round truncate to 3 decimal places and mill your work. And then I think this one would be 0.822299769. The last one would be 0.8664935. And then you have to go to your home screen and type all those in, and then I think you get the same answer. So it's kind of nice to be able to just do it all on here on your home screen without having to do them individually. And by the way, if you do them on the graph screen, it does take a little longer because they got to it shades it, which is cool, but just, unnecessary. So You got to make sure you're keeping more than 3 decimals in the middle of your word. If you don't, and even if you get lucky, I'm taking off points on your test. Okay? Final answer should be 3 decimal. Don't give me 6 decimals, because while that could be allowed, whatever decimals you give me for your final answer are eligible to be judged for accuracy. So if you give me 6, is your 6 decimal really accurate to 6 decimals? It's possibly not, because you didn't keep more than 6 decimals in the middle of your work. Same issue. Or your calculator actually doesn't do these perfectly and the accuracy is off. So anyways, that was a good challenging problem. There's a little bit of geometric strategy in here. How do you find a weird area, break it up into other areas that you can find by adding them, subtracting them, whatever. So good amount of work in there. You got to show the setups, okay, on your homework, on your tests, okay, on the AP tests. All right. Hope you guys are getting the hang of calculus problems now. And I think that's the last assignment for this unit other than pretest. Pretest is next, and that's a good worksheet to practice for your test.